Welcome back to the deep dive. Today we're jumping into something pretty exciting in the AI space, image generation.
Yeah, specifically a new model that's making some waves. It's called NextStep-1.
Exactly. And you know us, we love to get into the technical weeds, figure out how these things actually work under the hood.
Mhm.
So that's our mission today, same as always. We'll dig into the tech details, the implications, really give you a solid understanding of what makes NextStep-1 tick.
Right.
We're basing this on their recent paper, NextStep-1, toward autoregressive image generation with continuous tokens at scale.
It's from the Step-1 team.
Exactly. And this paper, it's quite a significant push for autoregressive models. You know, they kind of lagged behind diffusion models in some ways.
Right.
So we're going to break down the architecture, how they trained it, the performance numbers, all through that technical lens. We'll look at the engineering choices, the algorithms.
And hopefully uncover some of those aha moments.
Yep.
Definitely. We'll be talking about things like continuous tokens, flow matching, concepts that are really central to why this model is getting such high fidelity results.
Yeah.
And the challenges, too, the clever ways they got around them.
Okay, let's dive in then. So, NextStep-1. The paper kicks off by saying it's a 14 billion parameter autoregressive model. But what immediately jumps out is how it differs from the usual suspects.
Mm-hmm.
The paper points out this issue with current AR models, right? They either rely on really heavy, computationally costly diffusion models for continuous image data.
Or they go the other route.
Yeah, using vector quantization, VQ, for discrete tokens, but that has its own problems, doesn't it? Like quantization loss, where you lose detail.
Precisely. Quantization loss is a big one. You're basically forcing rich visual information into a limited set of visual words, so some nuance gets lost. And you also run into other issues like exposure bias, maybe suboptimal tokenization. It all adds up.
So the core question then is, what's NextStep-1 doing differently? How is it trying to push past these limitations in the AR approach?
Well, this is where it gets really interesting. NextStep-1's core idea is it trains on both discrete text tokens and continuous image tokens simultaneously. It's a unified approach.
Unified. Okay. So text and image data handled together in the same flow.
Exactly. And the key component for handling the images, the continuous part, is this thing they call the flow matching head. It's about 157 million parameters.
Right.
So instead of VQ, squashing images into discrete buckets or using a separate heavy diffusion model, NextStep-1 treats the image data as a continuous flow.
A continuous flow.
Yeah, which allows for, much more subtlety, more nuance in representation.
So it's not picking the closest visual word from a list. It's more like working directly with the raw visual signal.
That's a good way to put it. And the whole thing is built on the next token prediction idea, which is standard for LLMs, right? Predict the next word. Here it's predicting the next part of the image, but in this continuous space. So it generates patch by patch, guided by that lightweight flow matching head.
Patch by patch. Okay, that sounds quite different from diffusion models that often generate the whole thing more holistically.
It is. Diffusion models often work from a single semantic embedding to generate the whole image. This is sequential, patch by patch. And this unified, continuous approach is what gives it that high-fidelity synthesis they talk about, and also enables some really robust image editing, too.
Ah, right, the editing capabilities. I saw some examples in the paper.
Yeah, things like adding objects, changing backgrounds.
Yeah.
It all stems from this core architecture.
Okay, so if I'm understanding this right, it's less like building with Lego bricks, those discrete tokens, and maybe more like sculpting with clay, continuous tokens, infinitely adjustable. And the flow matching head is kind of guiding the sculpting tool.
That's a great analogy, actually. Yes, it allows for those smoother, more fluid adjustments.
So from a technical perspective, why is this shift from discrete to continuous tokens such a big deal? What specific problems does it really overcome compared to those VQ or diffusion-assisted AR models?
Well, moving to continuous tokens tackles a few key limitations head-on. First, there's that exposure bias issue I mentioned with discrete models.
Right.
During generation, if a model sees a sequence of discrete tokens it wasn't explicitly trained on, it can kind of go off the rails. The output quality drops. Continuous tokens offer a richer, smoother space, making it less likely to hit these unseen combinations. It's more forgiving.
Okay, so it smooths out the generation process.
Exactly. And second, it completely avoids that quantization loss inherent in VQ. You're not forcing the visual data into a limited vocabulary, so you retain more of the original information, the fine details.
Which leads to better quality images, presumably.
That's the goal. The paper explicitly talks about a performance gap that existed between AR models and top diffusion models, especially on image quality and consistency. NextStep-1's continuous token approach is designed specifically to try and bridge that gap. It's about working with the full visual signal.
Makes sense.
Now, what the paper doesn't spend a lot of time on, which is a really important technical trade-off to consider, is the computational side of things during training.
Ah, the cost.
Yeah. Handling these high-dimensional, continuous latent spaces, it's potentially much more demanding in terms of compute memory compared to discrete tokens.
So better quality, but maybe harder to train?
Potentially, yes.
Well-
There's likely a trade-off between generation quality and training efficiency. They get great results, but scaling this approach to even larger models in the future. Well, that raises questions about resource requirements. How do you balance that amazing quality with the training cost? That's something the field will need to keep exploring.
Right, the scalability question. Okay, let's get into the architecture itself. This is where it gets really interesting. The nuts and bolts. It's a 14B parameter model, transformer backbone. Can you break down the main pieces? The image tokenizer, the causal transformer, those two lightweight heads. What does each part do?
Absolutely. It's quite an elegant setup. So first up is the image tokenizer. Its job is crucial. Take the raw image and turn it into those continuous image tokens the transformer can actually understand and work with.
Okay, the input stage.
Exactly. And they didn't build this from scratch. They fine-tuned it from something called Flux VAE, which is known for really good image reconstruction. That's important. You need to capture the visual detail accurately in the latent space right from the start.
Makes sense. Use something proven.
Right. So it encodes images into 16-channel latents, and it does an 8x spatial downsampling.
Okay.
So think of a 256 by 256 image becoming a 32 by 32 grid. But each pixel in that grid isn't just RGB. It has 16 channels of information.
16 channels.
Yeah.
Wow. That's a lot richer than just color.
Way richer. It allows the model to encode much more complex information texture, maybe depth cues, abstract features, things that help create those fine details later on.
But doesn't that make it unstable? High dimensions can be tricky.
They can be. Yeah. And that's where some clever stabilization techniques come in. They use channel-wise normalization, basically making sure each channel has zero mean and unit variance.
Yeah.
Keeps things stable.
Okay.
And they also add stochastic perturbation. It's like adding a tiny bit of controlled noise adapted from sigma VAE. That sounds counterintuitive, but it actually makes the model more robust and helps create what they call a well-dispersed, normalized latent space. There's a hyperparameter, gamma, that controls how much noise is added.
Noise helps. Okay, we'll have to come back to that.
Definitely. Then there's this transformation step called pixel shuffling, or space to depth. It takes 2 by 2 spatial blocks from that 32 by 32 grid and kind of folds them into the channel dimension.
Bolts them in.
Yeah, so you go from a 32 by 32 grid with 16 channels to a 16 by 16 grid, but now each pixel has 64 channels, 2 by 2 by 16. The 16 by 16 grid is then flattened into a 1D sequence of 256 tokens.
Ah, okay. So that's how they feed the 2D image data into the 1D transformer?
Exactly. It's a smart way to handle that high-dimensional continuous data sequentially. Then you have the causal transformer, the main engine. It's initialized from Quinn 2.514b, a powerful decoder-only language model.
So they're leveraging existing LLM capabilities.
Precisely. Why reinvent the wheel? It gives them a strong foundation in language understanding and reasoning right out of the gate. The input sequence is very structured. You've got the text prompt, special tokens indicating the image area size, the start of the image, boy, the continuous image tokens themselves, and an end of image token, EOI.
Very organized.
And for positional encoding, they use standard 1D rotary positional embeddings. Interestingly, they found this simple 1D method worked well enough for the mixed text-image sequences, even though you might think 2D encoding would be better for images. They prioritize simplicity and efficiency there.
We should probably circle back to that choice, too.
Good point. Finally, you had the two lightweight heads. One is a standard language modeling head using cross-entropy loss for the text tokens. The other is the crucial patchwise flow matching head. That's the 157M parameter MLP.
Right, the one doing the image generation part.
Well, more like the sampling part. It takes the transformer's output for a given patch and predicts the continuous flow needed to denoise that patch from a noised version to its clean state. It's always conditioned on the transformer's hidden state, so it knows the context.
Okay.
And the overall training goal is just a weighted sum of the text loss and this visual flow matching loss, balanced by hyperparameters.
That's a really clear breakdown, thanks. But I'm still stuck on that 1D ROP decision.
For image data, which is inherently 2D, sticking with 1D positional encoding, beyond simplicity, does that potentially create blind spots? Could it struggle with really complex spatial arrangements compared to something using 2D encodings? That's a really sharp question. It hits on a potential trade-off. The paper suggests that for their specific autoregressive sequential generation process, where the 2D image is flattened into that 1D sequence, the 1D row PE was sufficient. The transformer is primarily learning the sequence of patches.
So the 2D structure is kind of implicit in the 1D order.
To some extent, yes. The way it's flattened preserves some spatial locality, and 1D row PE is definitely simpler and computationally cheaper than 2D alternatives, but you're right to ask if it's a limitation. It's certainly plausible that for images requiring extremely precise, long-range spatial reasoning, or maintaining perfect grid alignment at very high resolutions, a 2D-aware encoding could offer advantages. The paper doesn't show a direct comparison, so it remains a bit of an open question whether they sacrifice some potential spatial understanding for efficiency. Future work might explore that trade-off more.
Okay. And the other thing, those 16-channel latents, you mentioned they allow for richer representation but also need stabilization. What's the concrete benefit of 16 channels versus, say, just 4 channels? If 16 adds complexity and stability headaches, why push for that higher dimensionality?
The benefit really comes down to representational capacity. Think of each channel as carrying a different kind of visual information. With only 4 channels, you might capture basic color and structure, but with 16 channels,
you can capture more nuance.
Exactly, much more nuance. Finer textures, subtle lighting effects, material properties, maybe even abstract semantic features the model learns. That extra bandwidth allows the model to represent the image much more faithfully in the latent space.
Which translates to better final image quality.
Precisely. Higher fidelity, sharper details, more realism. If you want to render, say, the complex texture of wood grain, or the way light reflects off glass, those extra channels give the model the capacity to encode and then reconstruct that information accurately. So while it does introduce stability challenges, more dimensions are inherently harder to manage. The researchers clearly felt the gain in visual quality was worth tackling those challenges with techniques like channel-wise normalization and that stochastic perturbation. It's a deliberate design choice to push the quality ceiling for autoregressive models by giving them a richer internal language to describe the images.
Gotcha. Okay, so with that architecture in mind, how did they actually train this thing? The paper mentions a really diverse data set. Can you walk us through the different kinds of data they fed it? What was each part for?
Right, the training data is crucial, and they use a very diverse mix broken down into 4 main categories. It's like a balanced diet for the AI.
Okay.
First, a huge text-only corpus. 400 billion tokens from their Step 3 language model dataset.
400 billion. Wow. Why so much text for an image model?
To preserve the language understanding of that Qwen 2.5 backbone, you need the model to deeply understand the text prompts, especially complex or nuanced ones, to generate the right image. Strong language skills are foundational.
Okay, makes sense. Keep the LLM part smart.
Exactly. Second, the core image-text pair data. 550 million high-quality pairs. This is the bread and butter for learning text-to-image generation. They had a whole pipeline for this. Sourcing data widely, then rigorously filtering it.
Filtering for what?
Aesthetics, clarity, no watermarks, good OCR text detection, and crucially, strong semantic alignment between the image and text. They even recaption images using their own powerful model, Step-1 Turbo, in English and Chinese to ensure rich descriptions.
So quality control was key.
Absolutely.
Yeah.
Third, they added instruction-guided image-to-image data, about 1 million samples. This is vital for practical stuff, editing, restoration, controllable generation using inputs like ControlNet annotations.
So that's where the editing skills come from.
Largely, yes. They source this from specialized data sets and tools, again with very strict filtering based on quality, rationality, consistency, and how well the output matched the edit instruction.
Okay. And the fourth category?
Interleaved data. 80 million samples where text and images are mixed together naturally within a sequence. This helps the model learn richer associations.
Interleaved, like in a document or a web page.
Exactly. Or even video. They use general video data for world knowledge, tutorial videos using speech recognition and OCR for text-rich scenes, and multi-view object data for geometric understanding.
Multi-view data. Interesting.
And a really cool part here is their character-centric data set. They took videos, focused on specific characters, and generated captions describing their actions and interactions. This helps with things like multi-turn conversations and keeping characters consistent across generated scenes.
That's clever. Targeting a common weakness.
Very much so. It's an incredibly comprehensive data strategy overall.
No kidding. That sounds like an enormous undertaking just to prepare the data. So how did the actual training proceed? It wasn't just one big training run, right?
So,
The paper mentioned stages. Pre-training, post-training.
Correct. It was a carefully staged process, like a curriculum. First, they trained the image tokenizer itself, just fine-tuning that flux VAE for about 50,000 steps, getting the foundation solid.
Step 1, stable tokens.
Exactly. Then came the main flex. Pre-training in 3 stages, training everything except the frozen tokenizer.
Okay.
Stage 1 was about fundamentals. Fixed 256 by 256 resolution images, a mix of text-only, image text, and interleaved data. About 1.23 trillion tokens consumed here, learning basic image structure and text-image links.
Got it. Basics first.
Stage 2 ramped things up. Dynamic resolution training on images from 256 by 256 up to 512 by 512, using aspect ratio buckets for efficiency. They also enriched the data mix with more text-rich and video data. This stage used another 0.61 trillion tokens, building on stage 1 to handle more detail and generalize better.
Scaling up resolution and complexity.
Right. And the final pre-training stage was annealing. This was short but critical, just 1 epoch, but on a super high-quality subset of 20 million image-text pairs, filtered very strictly.
Like a final polishing step.
Precisely. To sharpen everything, image structure, composition, texture, aesthetics. Focusing on the best examples to refine the model's output quality.
Okay, that covers pre-training. What about post-training?
Post-training is all about aligning the model with human preferences and specific tasks. 2 parts here. First, supervised fine-tuning, SFT. This boosts instruction following. They used 5 million samples.
What kind of samples?
High-quality, human-selected pairs, instruction-guided editing data, and interestingly, data generated via chain-of-thought reasoning.
Chain of thought. Like the model thinks before generating.
Kind of. It involves generating intermediate reasoning steps in text before creating the image, which helps with complex prompts. And they also use distillation.
Distillation, learning from other models.
Exactly. They included images generated by other state-of-the-art models for complex or imaginative prompts. So next step 1, learn how other successful models handle tricky requests.
Wow, that's meta,
Yeah.
learning from the competition.
It's a smart way to transfer knowledge. The final step was direct preference optimization, DPO. Similar to what's used in LLMs, but adapted for images, inspired by diffusion DPO.
Aligning with what humans prefer.
Right. They generate multiple image candidates, score them, using human ratings or reward models like image reward, and create preferred rejected pairs to fine-tune the model further. They even did a self-call-to version of DPO, using that chain-of-thought reasoning to enhance the prompts before generation and scoring.
Good grief. That is an incredibly elaborate training pipeline. It really highlights the complexity involved. But going back to that huge text corpus, 400 billion tokens, even with weighted loss, is there a risk it biases the model? Does preserving language skills potentially come at the cost of some visual fidelity? Or is the weighting enough to keep the focus squarely on image generation?
That's a valid concern. You're essentially feeding it vastly more text data than multimodal data, numerically speaking. The key defense against that bias is the loss weighting.
Right, you said the visual loss is weighted much higher.
Yes, eVisual set to 1.0, while eText is only 0.01. That's a 100x difference. So during the actual multimodal pre-training, the optimization gradient is overwhelmingly driven by how well it generates the image tokens, not the text tokens.
So the text data provides the foundation, but the training actively pushes harder on the visual side.
Exactly. The goal isn't just to preserve language skills, but to leverage them as a powerful semantic engine to improve image generation. The weighting ensures the model prioritizes visual learning while benefiting from the linguistic understanding. It seems like a well-thought-out balance based on their results.
Okay, that makes sense. And the distillation technique, learning from other models' outputs, how does that work technically? Is it just feeding in pairs of prompt other model output image as training examples? Does it help NextStep-1 capture styles or handle concepts it wouldn't have otherwise?
Essentially, yes, that's the core idea. You identify prompts where other models excel, especially complex, abstract, or stylistically specific ones. You generate images using those teacher models. Then, those prompt teacher-image pairs become part of NextStep-1's SFT dataset.
So it learns to mimic the good outputs.
It learns the mapping from those difficult prompts to high-quality outputs, as demonstrated by the teacher models. It's not necessarily learning the style in the sense of becoming a perfect mimic of Mid-Journey, for example, but it's learning the generative patterns and solutions those models found for rendering complex concepts effectively.
Ah, okay.
If a teacher model is great at, say, generating intricate sci-fi cityscapes or photorealistic animal fur, NextStep-1 learns from those successful examples how to approach similar prompts. It accelerates the learning process for these complex cases by effectively transferring knowledge about what works from the broader generative ecosystem. It's a very efficient way to boost capability on challenging prompts during that SFT stage.
Very clever. All right, let's talk performance. The paper makes some big claims, saying it's state-of-the-art for autoregressive models. How did they back that up? What benchmarks did they use, and how did NextStep-1 actually perform, especially compared to those big diffusion models?
They used a pretty comprehensive suite of benchmarks trying to cover different aspects. For text-to-image generation, they looked at alignment and world knowledge.
Okay.
For image-text alignment, they used GenEval to test things like counting objects correctly, placing them right, spatial relationships. NextStep-1 scored 0.63, which went up to 0.73 with self-critique.
Self-critique helping again.
Consistently. On GenAI Bench, for general prompts, it got 0.88 on basic and 0.67 on advanced prompts, again boosted by self-critique. And importantly, they state this is competitive with some diffusion models like SD 3.5 large.
Competitive with diffusion models. That's a strong claim for an AR model.
It is. On DBG Bench, which focuses on long prompts with multiple objects, it scored 85.28, showing good compositional ability. Then on 1IG Bench, looking specifically at English prompts for alignment, text rendering, reasoning, style, it got 0.417.
How does that compare to other AR models?
Significantly better. The paper shows it clearly outperforms models like EMI3, 0.311, and Janus Pro, 0.267. So definitely pushing the soda for autoregressive approaches there.
Okay, clear light in the AR space. What about that world knowledge part?
Right, using the WISE benchmark. This tests factual grounding, understanding concepts. NextStep-1 scored 0.54, jumping to 0.67 with self-caught. And here's the kipple. They state, it exceeds most diffusion models on this benchmark.
Wow, better world knowledge than diffusion models.
According to this benchmark, yes. With a prompt rewrite protocol, it even hit 0.83 with self-caught. This suggests it's really good at integrating factual understanding into the images.
That's fascinating.
And quickly on image editing, they fine-tuned a version called NextStep-1 Edit. On benchmarks like GetItBench NN and ImEditBench, it achieved scores of 6.58 and 3.71 respectively, which they again describe as competitive performance against advanced diffusion-based models, showcasing its practical editing chops.
The numbers are definitely strong, especially the world knowledge claims and beating other AR models soundly. But I'm really intrigued by that world knowledge aspect. What does that mean technically for an image generator? How does a model even learn world knowledge and then use it to make a picture? It seems quite abstract.
It is abstract and crucial. For an image model, world knowledge isn't just knowing facts, like Paris is the capital of France. It's knowing what Paris looks like, what the Eiffel Tower's structure is, how light typically falls on Parisian streets, what kind of architecture is common. It's visual common sense tied to factual reality.
Okay, the visual manifestation of facts.
Exactly. And it learns this primarily from that massive image text data. Seeing millions of pictures of Paris captioned Paris teaches it the visual patterns. The interleave data helps too. The character-centric scenes teach it about typical actions and interactions. The tutorials teach about objects in real-world contexts.
So exposure to vast amounts of caption reality.
Plus, the strong LLM backbone. The Qwen 2.5 part understands the concepts from the text prompt, allowing it to retrieve or activate the relevant visual patterns learned from the image data. When you ask for a doctor in an operating room, the LLM part understands doctor, operating room, and their typical relationship, which then guides the visual generation based on all the operating rooms it's seen.
So it's a combination of language understanding and visual pattern recognition.
Precisely. And the self-contained results really support this. Making the model think in text first helps it organize that knowledge and apply it more accurately to the visual generation. It explicitly connects the linguistic concepts to the visual elements before drawing the picture.
That makes sense. It's accessing and structuring its knowledge before generating.
Right. Now, the paper doesn't fully detail the exact mechanisms inside the model. Is knowledge stored in specific neuron groups? Is it all emergent in the attention patterns? How does it retrieve visual facts so effectively? That's still an active area of research, understanding the internal knowledge representation in these huge multimodal models. But the performance suggests the mechanism, whatever it is quite effective here.
Okay, digging deeper into the paper's own analysis. They have this fascinating section asking, what governs image generation, the AR transformer or the FM head? That sounds like a really fundamental question about how this model works, What did they find?
Yes, this is a key part of their analysis, trying to pinpoint where the real magic happens.
Yeah.
They emphasize again that NextStep-1 directly models continuous image tokens autoregressively, unlike other approaches where an AR model might just provide conditioning for a separate diffusion process.
Right. The transformer generates patch by patch via the flow matching head.
Exactly. And their big finding here was based on varying the size of that flow matching FM head. They tested a small one, 40 M per amps, the base one, 157, and a large one, 528 M.
And did bigger mean better?
Surprisingly, no. The results, both quantitative, Table 7, and qualitative, Figure 4 showing generated images, were remarkably consistent across all three sizes. A huge FM head didn't really improve things over the small one.
Whoa, so the size of that image-generating head doesn't matter much.
Apparently not for the final quality. The implication is pretty strong. The heavy lifting, the core generative modeling of predicting the next image patch based on context is being done by the transformer backbone. The flow matching head seems to act more like a lightweight sampler, almost like the final layer in an LLM that turns hidden states into word probabilities. It translates the transformer's complex prediction into the actual continuous token. But the intelligence of what token to generate resides mainly in the transformer.
So the transformer is the artist, the FM head is just the brush.
That's a good way to think about it. The essential generative logic is in the transformer's autoregressive process. Now, one caveat. While the FM head size might not affect quality, its operation, the multi-step sampling it does for each token, likely still contributes significantly to the inference latency, the speed issue we discussed.
Right, small doesn't necessarily mean fast if it has to do complex work repeatedly. Okay, what else did they discover about what governs generation?
The other huge insight was the absolutely critical role of the image tokenizer. It's not just an input processor, its properties fundamentally shape the generation quality.
How so?
First, it's key to mitigating instability under strong classifier-free guidance, CFG. You know how strong CFG can cause artifacts like weird gray patches in some VAE-based models?
Yeah, I've seen those.
People used to blame 1D positional embeddings. But NextStep-1's team found the root cause is actually how small errors or shifts in the token distribution get amplified down the long sequence when guidance is strong.
A cascading error effect.
Exactly. And their solution, that channel-wise normalization in the tokenizer. By enforcing stable statistics, zero mean, unit variance, for each token's channels, it prevents this drift. It's a simple trick, shown clearly in Figure 5, but it allows them to use strong CFG without the image falling apart. A major win for AR models.
Wow, such a simple fix for a big problem.
Isn't it? Second, they found that a regularized latent space is critical. This is that counterintuitive point about noise.
Right, more noise during tokenizer training leads to better generated images, even if reconstruction gets slightly worse.
Precisely. They found that higher noise intensity, gamma 0.5, resulted in the best final images, despite having the highest reconstruction loss during tokenizer training.
Why would that be?
They argue the noise regularization creates a well-conditioned latent space. It makes the tokenizer's decoder more robust to small errors or perturbations in the latent codes, Figure 6, and it leads to a more spread out, well-dispersed latent distribution, closer to a nice smooth Gaussian, Figure 7.
So the noise forces the latent space to be smoother and the decoder to be tougher.
That seems to be the idea. It suggests that just optimizing for perfect reconstruction isn't enough. You need these regularization properties for good generation.
Fascinating.
And finally, they confirm the principle that reconstruction quality is the upper bound of generation quality. Basically, your generated images can't be much better than what your tokenizer can reconstruct from its latent codes. Diffusion models often use VAEs with high PSNR, 35. VQ models struggled here. NextStep-1 managed to pair their AR model with a high-fidelity continuous VAE, PSNR 30.60, bridging that gap.
So a good tokenizer is absolutely fundamental.
Absolutely critical. Its stability, regularization, and fidelity set the stage for everything the transformer does.
That finding about noise regularization improving quality despite increasing reconstruction loss, that really makes you think, doesn't it? Does it imply our standard loss functions, like MSE for reconstruction, are kind of missing the point? Maybe we should be directly optimizing for latent space, goodness, or robustness, not just pixel accuracy.
I think that's exactly the implication. It suggests that minimizing reconstruction error alone doesn't guarantee a latent space that's ideal for generation. A truly generative latent space needs other properties, smoothness, robustness to noise, good dispersion, that aren't directly captured by simple reconstruction metrics.
So we might need new training objectives.
Potentially, yes. or at least incorporate strong regularization techniques, like the noise injection here, even if they seem to hurt the simple reconstruction loss. It's about optimizing for the downstream task of generation, not just the intermediate task of reconstruction. It forces us to think more deeply about what properties make a latent space useful.
And the channel-wise normalization, so simple, yet so effective for stability, could that idea be applied elsewhere, like in generating sequences of audio data or other complex modalities where stability across tokens is crucial?
Absolutely. The core problem it solves, preventing the amplification of statistical shifts in a long autoregressive sequence, isn't unique to images. Any sequential generation task dealing with high-dimensional, continuous, or even discrete tokens could potentially suffer from similar instability.
Like audio waveforms.
Exactly. Generating raw audio or maybe complex spectrograms token by token. If the statistical properties drift too much from one audio chunk to the next, you could get glitches or unnatural transitions. Applying some form of per-token normalization or stabilization could potentially improve coherence and reduce artifacts there too.
Or even mixed modal sequences.
Yeah, imagine generating interleaved text, image patches, and audio snippets. Ensuring some statistical consistency for the tokens of each modality as they're generated might be key to preventing the whole sequence from becoming unstable. It's a general principle. Keep the token distributions well-behaved throughout the sequence. Definitely an insight with potential beyond just this specific image model.
Okay, no model is perfect, though. The paper is commendably transparent about limitations. What are the main hurdles NextStep-1 still faces? What do these challenges tell us about where autoregressive image generation needs to go next?
Right, the limitations section is always important. They highlight a few key areas. First, artifacts. Even with the stabilization, they still see some issues, especially when using the higher dimensional 16-channel latent space compared to, say, 4 channels.
What kind of artifacts?
They show examples in Figure 8. There's some local noise, blocky patches suggesting maybe numerical issues, sometimes global noise hinting the model might need even more training.
Yeah.
And interestingly, subtle grid-like artifacts.
Grid artifacts, like you can see the patches.
Possibly. They speculate it might be related to the limitations of the 1D positional encoding trying to capture 2D structure perfectly. They admit the underlying causes aren't fully pinned down yet. It raises that question again. Could different positional encodings or architectures help?
Okay, so visual quality isn't perfectly solved. What else?
Inference latency. This is a big one. That serial patch-by-patch generation is slow.
How slow?
On an H100 GPU, generating a 256 token sequence, like a 256 by 256 image, takes about 2.8 seconds. A longer 496 token sequence takes almost 46 seconds.
Oof. That's way slower than most diffusion models.
Definitely. The transformer decoding is the main bottleneck, but the multi-step sampling in the FM head adds up too. They suggest directions like using smaller FM heads, distillation for faster sampling, or adapting LLM speedup techniques like speculative decoding. But applying those to visual tokens might have unique challenges.
Yeah, predicting the next patch might be harder to speculate on than the next word.
Could be. Third, challenges in high-resolution training. Autoregressive models inherently need more training steps to converge at high resolutions compared to diffusion models that refine the whole image at once. And techniques used to help diffusion models scale, like time step shifting, don't really apply here because the transformer does the main work, not the sampler head. Designing AR-specific high-res strategies is still needed.
So scaling up is tough.
And finally, challenges in supervised fine-tuning, SFT. They found SFT is unstable on small datasets. Unlike some models that fine-tune well with a few thousand examples, NextStep-1 seems to need millions of samples for SFT to work robustly without overfitting badly or barely improving.
Millions. That makes fine-tuning for specific tasks much harder.
It does. Finding that sweet spot where it adapts to the new data without forgetting its general abilities is tricky with this architecture, especially on smaller datasets. It's a practical hurdle for deployment and specialization.
It really seems like the core autoregressive patch-by-patch nature creates both its strengths like that fine control and its biggest weaknesses, especially latency and scaling. Out of all those challenges, what feels like the most critical one to solve for AR models like this to really compete broadly with diffusion, especially given that speed issue?
I'd have to agree, the inference latency is probably the most significant practical barrier right now. The quality is clearly getting there, even competitive in some aspects. But 3 seconds, let alone 45 seconds, for a single image generation is just not feasible for many applications where diffusion models offer near-instant results.
Right, interactive use is out.
Pretty much.
Yeah.
Solving this likely requires fundamental breakthroughs in parallelizing autoregressive decoding for visual data, or perhaps radical new sampling methods. Speculative decoding is promising, but as we discussed, adapting it effectively from text to the continuous high-dimensional space of image patches might be non-trivial. Until they can drastically cut down that generation time, it will likely remain more of a research curiosity than a widely deployed alternative, despite the impressive quality.
And that SFT difficulty on small data sets, that's also a big practical issue. Does the paper offer any clues? Are there ways to make SFT more stable, maybe architectural tweaks or different training strategies? Or is this specific model just inherently data hungry for fine-tuning?
The paper doesn't really offer specific solutions for the SFT instability on small datasets. Your main observation is simply that it requires million sample scale data for robust improvement. This strongly suggests that, at least for this current architecture and training setup, it leans towards being inherently data hungry for fine-tuning.
So no quick fixes mentioned?
Not explicitly. It might be related to how the very broad pre-training creates internal representations that are resistant to shifting based on limited new data without destabilizing. Unlike diffusion models, where fine-tuning often adapts specific parts of the noise prediction network, fine-tuning the entire transformer here might be more delicate. Perhaps future work could explore parameter-efficient fine-tuning (PEFT) methods, like LoRa, applied to the visual generation context, or specialized regularization techniques for SFT. But based on this paper, the current answer seems to be, you need a lot of data to fine-tune NextStep-1 effectively.
Okay, well, what an incredibly detailed look at NextStep-1. We've really gone deep into the continuous tokens, that critical image tokenizer, the clever stabilization tricks, the complex training. It's clear they've made huge strides for autoregressive image generation.
Definitely push the boundaries.
And some fascinating insights, too, like the transformer doing the heavy lifting, not the generation head, and noise actually helping quality. It really makes you question some standard assumptions. What other unexpected tricks might be out there?
Absolutely. This work hammers home just how vital that initial tokenization and the properties of the latent space are, maybe even more critical than the final sampling mechanism in these AR systems. Optimizing those foundational components seems key for the future.
Well, that wraps up our deep dive into NextStep-1. If you found this breakdown of AI research fascinating, you can always find more on our webpage, neuralintel.org. We're also on YouTube with more discussions.
Keep exploring.
Until next time, keep learning, keep questioning, and keep digging deeper.